right, combinatorics. Hope you guys are doing well. We have an exciting time together here, prepared, talking around the topic of Rook polynomials once again. Okay, and I actually am excited. If this stuff doesn't really get your combinatorial juices flowing, well, what hope do you have? So this stuff's exciting, it's fun, it's kind of a culmination of a lot of ideas, and so I hope that you'll enjoy it. So today, just by way of review, first of all, we have this theorem here that tells us how to use the Rook polynomial of a given board and how we can break it down into subboards that do not interact with each other in terms of, you know, if I place a rook on board 1, that it has any chance of attacking the rook on board 2, okay? Then the Rook polynomial of the entire board, if it can be decomposed into these two subboards, is just the product of the respective Rook polynomials of those two non-attacking subboards, okay? And then, then we had this theorem that says the number of ways to arrange indistinct objects when there are restricted positions is equal to n factorial minus, okay, where if B here is representing the restricted positions themselves, it's the subboard of the checkerboard, okay? So you have to subtract off the number of ways to place one rook on the board times n minus 1 factorial, and you have to add back in the number of ways to place 2 rooks on the board times n minus 2 factorial, etc. Okay? And this formula, if you'll recall, came from the principle of inclusion, exclusion. Now, we had a little bit of time in our class session, and again, I am constantly uploading things that have taken place, you know, related to this class, and either in the way of lectures or discussions that we had in our classroom Zoom sessions. I'm uploading all of that to Canvas, so you can find all of that information there. And I believe it was Ilona that asked, hey, you know, what's the strategy for counting things inside of a given board? And for that, it really does kind of work to maybe start at the leftmost column of a subboard and just think about what happens if I place a particular rook in each one of those positions individually. And then once you're done with column 1, move over to column 2 and don't put anything in column 1 because you've already taken care of that. And you move like from left to right. I think when we were in class, we actually moved from right to left, okay? Unfortunately, I don't know if that part of the classroom session actually got recorded, but I did do something like that in one of the lectures. That was the strategy that I was using. So this was, this thing came from the principle of inclusion exclusion. Each one of these rook numbers can be gotten at through subboards if indeed the board can be broken down into subboards. But there are situations that arise where even those subboards are too complicated to deal with. So what do we do in such a situation? Okay, so that's what we're going to talk about now. So what happens if you can't decompose the board and it's still too complicated? Okay, well this thing right here isn't really an example of too complicated of a board. Let's just be honest. But it's just here to illustrate what we might try to do. And here's what we do. So what you try to do is you try to choose a box or a square in the board that that really does, if it weren't there, then we'd be able to decompose the board. So yeah, that's what this square right here does. Look at it, it's kind of at a corner, and you can tell that if this weren't here, if this square weren't here, then this board here and the remaining 3 squares up here would be decomposed from one another. There would be no more, there would be, they wouldn't interact with one another in terms of placing rooks in these 3 squares versus these 2. And then we would have an easier go at trying to count things. So if I choose this square right here, S, okay, let's let B sub S be the board with that square missing, okay? So if this thing, okay, if this thing is missing, of course, then I just have 2 boards that don't interact. I would have these 3 squares and these 2 right here. Okay, so how many ways, and by the way, our BS of BS star, that's what you get if you actually eliminate the row and the column that S belongs to. Okay, so BS is the board with S missing, and BS star is the board with the row and column containing S removed. And either one of those is going to break the board up into non-interacting subportions, okay? That is, you can see that fairly easily. You want to find a square where that happens. And essentially, BS is the board you get where you've decided, I am not going to place a rook there. And if I don't place a rook there, then that square might as well be gone, and I might as well just be dealing with the decomposed board. Okay, so that's the thinking on B sub S. Okay, is that if I remove S, then I still have to place all the rooks on the other squares, and they're all available to me. On the other hand, with BS star, I'm eliminating the row and the column that S belongs to. And if I do that, what that basically means is I'm thinking of placing a rook on that square. All right, so, and if I place a rook on that square and I eliminate the row and the column, then I'm going to get a remaining board in which I still have to place k minus 1 more rooks, because I placed 1 rook here and I would have to place k minus 1 elsewhere. Okay, so that discussion we just had shows that the number of ways to place k rooks on the board B, where B is all this, is the same as the number of ways to place k rooks on the board BS. So that means I eliminate this. That means there's no rook on S, right? I'm not putting a rook here. That means I can put a rook anywhere else. So I still have to place k rooks on BS if I want to get k total. Okay, plus, okay, this is the other option. You place a rook on S, which means you have to eliminate its row and column, which means you get BS star, and you still have to place k minus 1 more rooks. Okay, so that's this relationship between the rook number for B and the rook number for BS and BS star is this. Hopefully that makes good sense. Okay, let's see. How does that affect, okay, going down here, how does that affect the rook polynomial? Well, the rook polynomial for B is given by this sum, and then I just invoke I invoke this relation that we just came up with up here. Okay, I invoke that relation, and by the way, I only invoke it you know, obviously if I invoke it for 0, for r sub 0, this thing is going to be 0 right here, because this would be r sub minus 1. What in the world is going on here? So that's gone. Okay, so when I invoke that thing, really, I invoke it, the x to the k distributes to that sum, but really I only need to start this sum at k equal to 1, right? There's like boldface type right there. You see that? Okay, so k equal to 1, r sub k minus 1, which is really r sub 0 bs star x to the k. Okay, and then what's going on here? Well, this sum right here, notice that the power on x is always like 1 higher than the subindex right here. So here what I'm doing is I'm kind of shifting the index down to 0 because this really starts at r sub 0. I'm factoring out an x so that this subindex matches with the power on x. And that has the effect of I can really start this thing from 0 now, go from 0 to infinity, and there's an extra x sitting right here. Okay. Well, what in the world is what is this? What's that? What's this first summand? Well, that's just the Rook polynomial for b sub s. And what's this second summand? Well, this is x times this right here is the Rook polynomial for b sub s star. Okay, and there it is. That's the general relationship that we have between the original Rook polynomial and the Rook polynomial where we have focused in on some square that subdivides the board. And then once we've done that, it makes it much easier. We can deal with this much easier because b sub s, because of the way we chose s, that's going to be easier to decompose. Okay, and use our Rook polynomial magic on this. And similarly here, I mean, b sub s star is even more dramatically reduced in complication because there you've eliminated not just s, but you've eliminated s along with its row column. Okay, so this is an actual problem from the book here, but I want to work through this. Now there was like a couple of typos. I fixed them and I re-uploaded the combinatorics notes. So you may notice like I accidentally had like C4 going to C3 or something, but that's not how I came up with this. I was continually shifting the last column to the second and then to the third column, and I swapped row 2 and row 3. That's why you see LN becoming NL here. Okay, so this is a problem in the book. I mean, they talk about 5 different cars and officials for some kind of parade or something. And these are the restrictions on the Escort, Lexus, Nissan, Taurus, and Volvo. Okay. So these are the restrictions, right? There's some made up situation. But in the end, all I've done is I've shifted stuff around in such a way that, it's easier to see what's going on. And immediately you're like, oh man, there's no way to like decompose this board. No matter what I try to do, there's interacting squares, right? There's interacting entries. So, so we have this, okay? And we come down here and we're like, okay, let's draw this board. Is there like a square where I can divorce one part of the board from another part of the board? Well, yeah, there are several choices, but one such choice is this guy right here. So let's hone in on this square. This is like the entry corresponding to column 4 or official number 4 and the Lexus. Okay. So that's this entry right here. We hone in on this, we hone in on that, and we say what happens with that? So for BS, so what about the Rook polynomial for BS star? Now BS star means I eliminate the row and the column corresponding to this, or the column and the row corresponding to this. And that's, oh man, how easy is that? So the Rook polynomial for BS star is easy to get since it divides into 2 small pictures. Okay, it's like this group of 4 squares right here. Okay, this group of 4 squares right here, which I'll call BS1 star. Okay, so that's these 4 squares right here. Okay, and one with 2, which is, you know, since I'm eliminating this column and this row, these 2 squares are S2, okay, BS2 stars, that board. Now, in theory, I could have, I could have had, you know, I could have said that this is its own board and this is its own board, but why? I mean, this is easy enough to deal with on its own. Okay, so if I want to, like I say right here, just a general note, the number of rows and the number of columns always give upper bounds on the number of rooks that can be placed at one time, right? So if I have only 2 rows or 2 columns, I can't place more than 2 rooks at a time, okay? So that's sort of obvious, like, right, if a board had 2 rows and 5 columns, then the most number of, or 2 rows and 70 columns, the most number of non-attacking rooks I could possibly place would be 2, because I would only have 2 rows to work with, and for them to be non-attacking, you know, that's it. I would only be able to place 2 rooks at a time. Okay, one in the first row and one in the second row. Okay, so that's a general rule of thumb that you can always take to the bank. All right, so in trying to compute BS star, we look at BS1 star. Okay, remember S1 is this, or BS1 star is this, and BS2 star are these 2 boxes. Okay, so how many, okay, so what's the rook polynomial for BS1 star? Well, obviously the number of ways to place 0 rooks is just 1. How many ways are there to place 1 rook? Well, 1, 2, 3, 4, right? Just the number of squares. How many ways are there to place 2 rooks on BS1 star? 2, or 2, you know, how many ways are there to place 2 rooks on BS1 star? Well, I either place a rook in the upper left square and one in the lower right, or one in the lower left and the upper right. That's the only 2 options, which is why this is 1 plus 4x plus 2x squared. Okay, 4 ways to place 1 rook, 1 way to place no rooks, 2 ways to place 2 rooks. Okay, what about BS2 star? Well, that's easy. That's these 2 squares. There's 1 way to place 0 rooks. How many ways are there to place 1 rook? X to the first power, 1 rook. 1 here, 1 here. So there's a total of 2 ways to place 1 rook. And then what about 2 rooks? Well, that's easy. You just place 1 here and 1 here, and that's just 1 way. Okay, so that's why there's a 1 next to x squared. Okay, so Rx BS star, and remember BS star means I eliminated this and this, is the product, using that theorem, not this theorem, but this one way up here, this one right here. If I've decomposed it into things, I just multiply the respective rook polynomials to get the rook polynomial for the whole board. Okay, so Rx of BS star is the product of those rook polynomials we just computed. Yeah, so that's 1 plus, you know, 2x plus 4x is 6x. How do I get x squared? So it's going to be x, 1 times x squared is x squared, 2 plus 8x squared plus 2x squared is 11x squared total. And I'll let you work out the other one. Well, okay, so cube. How do I get a cube? I can do 2x squared and 2x, which is 4x cubed, or 4x and x squared, which is another 4x cubed, for a total of 8x cubed. And then finally, 2x squared times x squared is 2x to the 4th, right? So there's your rook polynomial for BS star. Meanwhile, okay, meanwhile, sounds like some kind of comic book thing here, but meanwhile, BS BS, okay, B sub S, now all that is like, you know, you get rid of this guy, right? Remember, BS means I'm just eliminating S itself. I'm not eliminating its row and column anymore, okay? I'm just eliminating that itself, but that still divorces the boards, okay? And I basically have 5 squares like this, and then I have 4 squares over here, okay? So that's what BS is. It's 5 squares on the left and 4 squares on the right, yeah? So meanwhile, BS divides into 2 smaller pictures, BS1 and BS2 of sizes 5 and 4 respectively. Yeah, so that's what I mean. So S1 is, BS1 is the board S1 is this, okay, without S, and BS2 is those 4 squares right there. That's what I'm talking about. That's what I'm talking about, okay? We go down here, RX BS1, I claim it's this. Let's see if we can figure this out. So apparently, as always, there's 1 way to place 0 rooks, 5 ways to place 1 rook. We know that because there was 5 squares. 4 ways to place 2 rooks. Okay, so let's see if that's true. 4 ways to place 2 rooks in here. 4 ways to place 2 rooks. Well, if I put a rook right here in the first row, okay, then there are there are 1, 2 places I could place a second rook, okay? And if I place a rook right here in the first row, then there are 1, 2 places I could place a second rook. Okay, so that gives me a total of 4 ways to place 2 rooks on that subboard, which is what it says. Okay, next, what about the rook polynomial for BS2? Remember, S2 is these 4 squares right here. Okay. Well, okay, so how many ways are there? Let's just stay right here. How many ways are there to place 1? Of course, 1 way to place 0 rooks. How many ways to place 1 rook? Well, 1, 2, 3, 4. Okay, so there should be a 4x. Okay, well, what about 2 rooks? All right, so I could place a rook here. That eliminates this column and row. And I would have to place the second rook here. So there's 1 way, okay? Okay, so that if I place a rook here in this first column, that gives me, there's only 1 place I can go. And I have to place a rook in this first column. So the other place I could put it is right here. And if I do that, if I do that, I'm seeing 1, 2 places that I could put a second rook. So I had one situation where I place a rook here. So the second one has to go here. And I saw 2 situations here. So I'm seeing 3 ways to place 2 rooks in this little board of 4 squares. 3 ways to place 2 rooks, which is exactly what's written right there, okay? And then, of course, the rook polynomial for B sub S is just the product of these 2 rook polynomials. And let's just make sure this is correctamundo here. Let's see, of course, you get 1. How do I get x? Well, 4x plus 5x is 9x. How do I get x cubed? Well, 5x times 3x squared is 15x cubed, plus 4x times 4x, 16x cubed. So wait a minute here. Is this, I think, oh, x squared. I think this is supposed to be an x squared, everyone. I'm sorry. Okay, so that's a little typographical error, okay? So this, for x cubed, it is 31 because you have 5 times 3, which is 15x cubed, plus 16x cubed, which is 31. Okay, I'll fix this in the notes and send that back out. That's a typo. And how many ways are there to place 2 rooks? This should be a 2. How many ways are there to place 2 rooks? Well, it's going to be 3x squared plus 20x squared, which is 23x squared, plus 4x squared, which is 27x squared, which is what that is. And finally, how many ways to place 4 rooks? Well, it's 3 times 4, which is 12. All right, so we have that. And we have the one from up here, Rx bs sub s star, okay? And down here, I actually have the correct the correct power on this. Okay, so that's good. So what happens here? The Rxb is going to be Rxbs. I'm just using this identity up here, Rxbs plus x times Rxbs star. Okay. So I have Rxbs, which is this, okay, plus x times Rxbs star. Okay, I just want to make sure that there's no other typos lurking here. I don't think there are. Okay, so what do we get? So of course 1 plus, okay, x, 1x plus 9x is 10x. 27x squared plus 6x squared is 33x squared. 31x cubed plus 11x cubed is 42x cubed. 12x to the 4th plus 8x to the 4th. When I distribute the x, gives me 20x to the 4th plus 2 times x to the 5th. That is remarkable. Look at that thing. 1. So that means there's 10 ways to place 1 rook. Of course, 1 way to place 0, 10 ways to place 1, 33 ways to place 2 on that obnoxious board up there, 42 ways to place 3, 20 ways to place 4, and 2 ways to place 5 rooks. Amazing. And so what's the formula going to be? This was a 5 by 5 situation, wasn't it? 5 rows, 5 columns. This was a 5 by 5 situation. So it's 5 factorial minus the number of ways to place 1 rook on bad squares, which is 10 times 4 factorial, plus the number of ways to place 2 rooks on bad squares times 3 factorial, minus 42 times 2 factorial, plus 20 times 1 factorial, minus 2 times 0 factorial, which is all those numbers are coming directly from that rook polynomial. That is amazing. And if you do the computation itself, I think I did this right. You get that. So I mean, let me see here, just to make sure, not going crazy here. Let me pull up. Wolfram Alpha. Okay, so hang on a second. Let's do that. Okay, let's see. I'll pull up Wolfram Alpha here. Okay, and we'll do the computation real quick. Pull it up over here so I can actually see what's in here. Okay, so in Wolfram Alpha, it's 5 factorial minus 10 times 4, 10 times 4 factorial plus 33 times 3 factorial minus 42 times 2 factorial plus 20 times 1 factorial, it's sort of silly, minus 2 times 0 factorial, okay? And I got 12, which is exactly what's over here, okay? Which is exactly what is over here, There it is, 12. Okay, so I'm going to stop this now. Hopefully that makes good sense. This is just a further tool to put in our back pockets to help us count ever more progressively complicated things, but we've really systematized the way in which we can deal with restricted positions. Very, very powerful tools indeed. Indeed. All right, so I'm gonna stop this for now, and I'll see you guys soon.